So you've got a couple examples here of a geometric sequence. And you're probably good enough to spot the pattern as to what you do to get from one term to the next, from here to here, or here to here. What is it that I'm doing to get from one term to the next? Multiplying by 3. So you're multiplying by 3 here, 3 here, 3 here. So you can figure out the next one, that'd be 324. How about up above?
Divide by 2.
Divide by 2. You could also say multiply by what number? Multiply by a half. So in each of these cases, if you take this number and divide it by this number, 6 divided by 12, 12 divided by 24, you get a half. Or 36 divided by 12, or 12 divided by 4, 108 divided by 36. The second number divided by the first number is always going to give you this value of r, which is your common ratio. Common ratio. And that's what defines a geometric sequence. You're multiplying by one constant term to get from one to the next. So that value is your r. Let's see if we can figure out what the general form of an arithmetic sequence is. So the general form, and I'm not going to go too slow on this because there's a few things that I want to get to at the end, and I don't want to short myself on time. So maybe you want to just relax for a moment. Let's take a look at the second of these sequences. A sub 1 was 4, then a sub 2 was 4 times 3, which gave me 12. And you know, I don't need to write it as 12, let's just leave it as 4 times 3. A sub 3 was 4 times 3 times 3 again, which is 4 times 3 squared. A sub 4, well, I'm going to multiply this by 3 again, so it's going to be 4 times 3 times 3 times 3, or better yet, 4 times 3 cubed. And maybe you're starting to pick up on the pattern here. The goal is to figure out, well, what's the general term going to look like? What's that general term going to be for this particular sequence? The thing to do when you're trying to find a pattern is take a look at your subscript and then look at things like here. 3 and then a 2. Or a 4 and then a 3. A 5 and a 4. Now there's other things in this that kind of stay the same, like 3 stays the same in all of these. Or 4 stays the same in all of these. But some of these things are changing along with your subscript. So what's the general term going to be? Well done. Wow, that was more general than I expected. In this particular case, it's going to be 4 times 3 to the n minus 1. In general, a sub n is going to be a sub 1, your first term, times r to the n minus 1. So well done. Yeah, so those terms stayed the same. The only thing that's changing is n. Put this with your list, your growing list of formulas for chapter 12. This is the general form of a geometric sequence. General form of a geometric sequence. Okay, so let's do some problems with these things. Starting with example A here. So they give you the first term of a geometric sequence and the common ratio. So for example A, a sub 1, now like I said, WebAssign often will write it as just a, not a sub 1. A sub 1 is -4, r is -5. Let's write out the first few terms of this sequence. Well, let's first write the general form. The general form is going to be a sub n is a sub 1 times r to the n minus 1, or -4 times -5 to the n minus 1. Okay. A sub 1. Well, we already know that. That's -4. A sub 2, maybe you go to the formula. It's going to be -4 times -5 to the 2 minus 1. Well, 2 minus 1 is the first power. So -5 to the first power is just -5. -4 times -5 is positive 20. Now you can get your calculator to do these things. There's nothing wrong with that at all. Maybe from last week you're still in sequential mode, maybe you're not. If you are, great. If you're not, that's fine too. Let me put my mode back in sequential mode. This means that it's going to expect integer values for n. So when I type in my formula, I can type in -4 to the parenthesis -5 raised to the n minus 1. Now I can just go to the table and type in any values that I want. I don't need u sub 1 in this particular case because this is an explicitly defined sequence. It's not a recursive sequence. Go to my table. I'm going to delete all the values here. Just start with 1, then 2, then 3, and 4. But this is kind of overkill. I think you can kind of see how to get from one term to the next. You're multiplying by -5. So -5 times that gives me -100. -5 times that gives me positive 500. And that's it. That's all they're asking for. What do you think? Can I give this one some love?
Yes.
Yeah? Okay.
That was easy.
Yeah, I mean, not bad. All you're looking for is this and these. Beautiful. Let's try another one. It can't all be this easy. So example B. The first 4 terms of a sequence are given. Determine whether these terms can be terms of a geometric sequence. So 1750, and then -350, 70, -14, dot, 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 dot. If so, what's the general term of this sequence? Well, the first thing I want you to do, and this is going to ask you to think a little bit, is determine, is this an arithmetic sequence? If it is, great. If it's not, great too. But how would you decide if this is an arithmetic sequence? Think about it for a second, and then turn to a neighbor and say, it is or isn't an arithmetic sequence because. Try to come up with an answer that would make me happy. Is it an arithmetic sequence? This is something that you're going to have to face a lot while you're working on your homework and on your exam. It's because I'm not going to give you, something and say, here's an arithmetic sequence, determine what D is, or here's a geometric sequence, determine what R is. You're going to have to be able to look at these things and decide for yourself. So if in its arithmetic sequence, then what would have to be true?
The difference of figures.
The difference would have to be the same. So this minus this, that gives me a common difference of -2100. The common difference here, let me do it this way. The common difference here 70 minus 350 is 420. These aren't the same. They have to be the same if it's an arithmetic sequence, and they're not. So it's not an arithmetic sequence. Next thing to look at is it a geometric sequence? This time I want to look at R. R is going to be the ratio of these things. So it's going to be negative 350 over 1750. And I want to compare that to R over here, which is going to be 70 over negative 350. Do I get the same ratios for both of these? Well, maybe you're not really that keen on working these numbers in your head. That's fine, no big deal. Take out your calculators, make your calculator earn your money. So negative 350 divided by 1750 gives me negative 0.2. What about 70 divided by negative 350? Oh, I get negative 0.2 again. What is that as a fraction? Because your instructor likes fractions, negative 1/5. So you're multiplying by negative 1/5, or essentially dividing by negative 5 to get from one term to the next. So is this a geometric sequence? Yes, absolutely. So this is a geometric sequence. R equals negative 0.2. So I can rewrite this now as a sub n equals a sub 1 times r to the n minus 1. In our particular case, 1750 times negative 1/5 to the n minus 1. Okay. Let's look back and remind ourselves what they wanted here. Yeah, they just wanted the general form of a geometric sequence. So looking pretty good there. We got a sub n. That's it. By the way, an easy question to add on to this would be, what's the fifth term in this geometric sequence? How would you get the fifth term? There's two ways I can see to do it right from here. I'm curious to see which one you would take. How would you get the fifth term? Anyone? Ella?
Multiplied by negative 1/5.
Yeah, you just take this and multiply by negative 1/5. So a negative times a negative is going to be positive, and the other part is 14 divided by 5. Just leave it as a fraction like that. So a sub 5 is going to be 14 over 5, or 2.8, whichever one you prefer. Doesn't matter. I like fractions better. All right, but that's a bonus. All they were asking for is the general term. Let's step it up a little bit. So determine the common ratio, the fifth term, and the nth term. So, yeah, the common ratio here is going to be a little bit more challenging. So our sequence is 4 and then 8/5, and then 16 over 25, and then 32 over 125, and so on. So we want to find D, no, excuse me, find R and a sub n. Those are the two things we're looking for in this particular example. Okay, let's do that. Let's find both of those things. Now what you should be looking at first is what's the common ratio. R would be 8/5 divided by 4. And then you've got to make sure that you have a consistent common ratio. So that I should have that common ratio again. How would I calculate R for this one?
25 over 8 over 5.
Perfect. 16 over 25 divided by 8 over 5. Now that becomes a little bit more of a pain to do on your calculator. You can do it. I mean, you can do this other ways, and I'll talk about that in hindsight. But just use some parentheses. 16 divided by 25, parentheses divided by, parentheses, 8 divided by 5. Again, you're going to get yourself a fraction, and you can turn that, or excuse me, you give a decimal, you can turn that into a fraction by hitting the math key and then enter twice. So R in this first case, or the second case, is 2/5. And guess what? In the first case, it's also 2/5. Because those match and you're multiplying by 2/5 to get from one term to the next, that means this is a geometric sequence. Quick review question. What would be true if this was an arithmetic sequence? How would it be different?
The distance would be equal.
Yeah, the number that you add to get from one to the other, or I like the way you said it, the distance between these would all be the same. But it's not. If you subtracted this from this, and this from this, it'd be different. So this one's a geometric sequence. I need a sub n. What's a sub n going to equal in this case? Ella?
4 times 2/5 to the power of n minus 1.
Perfect, perfect. Now, quick question for you. If I wanted a sub 5, are you going to take and plug in a 5 here? Or are you just going to multiply that by 2/5? Which one seems easier? So 2 times 32 is 64. 5 times 125 is 625. I like Robert's idea. We'll just multiply by 2/5. Sounds easier. Nice. Okay, let's keep going. Find the indicated terms of the geometric sequence with the given description. The fourth term is 12, and the seventh term is 81 over 16. Find the first and nth terms. This one's going to require a little bit of thought. Example D. So let's write down a sub 4 is 12, and a sub 7 is 81 over 16. I want to find a sub 1 and a sub n. Well, I know the general form of a sub n has to be a sub n is a sub 1 times r to the n minus 1. Well, let's think here. If I know that, 12 would be a sub 1 times r to what power?
Four minus 1.
4 minus 1. Let's call it a 3. Yeah, 4 minus 1. Nice. Sydney, how about a sub 7? What should I write here? All right. Jason?
R of 6.
Yeah. A sub 1 times r to the 6th power. Just go into that n minus 1 power here. N is 7. Now that gives me 2 equations and 2 unknowns. So Now, these aren't linear equations. I can't solve this with Gauss-Jordan elimination or Cramer's rule or something like that, but I can still solve them. If you have two unknowns and two equations, that's pretty much what you need. So here's a little trick, and it's a way to get rid of the a sub 1 term. I'm going to take the second equation and divide it by the first equation. So let's take 81 over 16 equals a sub 1 times r to the 6th, and divide it by 12 equals a sub 1 times r to the 3rd. Now, why would I do that? What benefit does that give me in coming up with this really big messy thing? Do you see any simplification? How about on the right hand side? Is there any simplification here? Just look at that as a fraction.
Does the R to the 3rd power cancel out?
To an extent, yeah. Let's do the easier stuff first though. What else is easy to cancel? A sub 1. That cancels right away. And Jacqueline spied the fact that I've got r to the 6th divided by r to the 3rd. What happens? You don't divide this, you subtract the exponents, right? That gives me r cubed. Now on the left hand side, you're going to end up with 27 over 64. Just trust me on that one. But that still doesn't tell me what r is. How am I going to get r?
Take the cube root of 27 over 64.
Good. R equals the cube root of 27 over 64, which is 3/4. Yay. All right, so that's one of the things I needed to know. I needed to know what R equals. Okay. So if R equals 3/4, does that help me out anywhere?
To get closer to knowing what A minus or what A1 is.
All right, that should help us get closer to knowing what A1 is. I agree. So what can I do now that I know that R is 3/4? Yeah, I plug in R. Let's plug in R into the first equation, right? Plug in R into 12 equals a sub 1 times r to the 3rd. Or in other words, 12 equals a sub 1 times 3/4 to the 3rd power. That's 27 over 64. How am I going to solve for a sub 1?
Multiply by reciprocal.
Yeah, well done. Multiply by the reciprocal. Perfect. So times 64 over 27 times 64 over 27. And I'll end up with 256 over 9 equals a sub 1. Again, take out your calculators as needed.
Yep.
So overall, I know what R is and I know what a sub 1 is. A sub n is going to be 256 over 9 times 3/4 to the n minus 1 power. Whew. All right. All right, that was a good one. I like that one. Comments or thoughts on that one? Is there something that maybe I did a little too quickly, then you got behind in the notes or something, anything I can help out with on that one? Okay. Jesse, thumbs up? Okay, all right, Reagan, thank you. All right, let's keep going. So we're gonna move on to something we did with arithmetic sequences, and that is we summed them up. We added them up and figured out what the sum was. So let me tell you how to sum the first n terms in a geometric sequence. The first n terms in a geometric sequence. Okay, that's a good one. We'll call that S sub n like we did before. This time the formula is going to look a little bit different. It's going to be a sub 1 times 1 minus r to the n over 1 minus r. So kind of like the last one, you need to know what n is. This time you need to know what r is, and of course a sub 1. Let's see if we can't apply that to this problem right here. Okay, let's see about that. Actually, you know what? Here, let's try this one down here first. So we'll do example H. Although I guess, yeah, we'll do example. I guess as we're looking at it, we'll call it example E. Yeah, actually we can do example E here. Yeah, that's not too bad. Do example E. I want the sum from I equals 1 to 5 of 8 times r to the n power, or r to the I power. So this is what you're going to see at home. Going to be 8 times 2 to the I minus 1 power. When you're given these kind of summations, it's not a bad idea to write out the first few terms just to get a handle on what kind of a series you're working with. Now, one thing you might pick up on is that sometimes I'll use the word series, sometimes I'll use the word sequence. It depends what you're doing. If you're adding up a bunch of terms, you're summing a series. But if you're just listing the terms, then you're working with a sequence. So a sequence is the list of terms, the series is the sum of the terms. In this particular case, it would look like this. At I equal 1, you'll have 2 to the 1 minus 1 power. Well, that's 2 to the 0 power. What's 2 to the 0 power? 1. So I get 1 times 8, which is just 8. If I put in a 2 here, 2 minus 1 is 1. So I get 2 to the first power times 8 is 16. And then times, plugging in I equals 3, I get 2 squared. 2 squared is 4 times 8 is 32. So it's looking pretty convincing. What are you doing to get from one term to the next in this series? Here to here, here to here.
Multiplying by 2.
Yeah, you're multiplying by 2. So you have a common ratio of r equals 2, r equals 2, equals 2, etc. So you don't necessarily need to go back to the formula for each of these. Times 2 again is going to be 64. Times 2 again is going to be 128. I mean, so you could just add this up. You get 248 just by giving it the eyeball test. But let's practice the formula. Just expect bigger numbers on an exam. So with the formula, I'd want S sub 5. Now accordingly, S sub 5 is going to be A sub 1 times 1 minus R to the 5th power over 1 minus R, which in our case is going to be 8 times 1 minus 2 to the 5th power over 1 minus 2. Now I know this formula seems like a big pain here compared to what we just did. It is, I won't lie to you. 1 minus 32 is negative 31 over negative 1. The negatives cancel and I get positive 248. Problem is you can't always rely on just being able to add them up. Sometimes you need to be able to do something a little bit more expeditiously.
Is there a way we can do the summation stuff on our calculator?
There is a good way to do it. If I get a chance, maybe at the end, I'll try and show you how you can do this on your calculator. But keep in mind, on an exam, two things are gonna be true. One, I'm gonna make that a much bigger number. And two, I'm gonna wanna see the work of you checking it, or of you showing me the work, all right? If you wanna check it on your calculator, I'm totally fine with that. I've been consistent with that throughout the whole course. If you can check things on a calculator or decimals, great. Nothing wrong with that. But let's take a look at it. Let's take a look at a different one that requires us to use the formula. Actually, no, we did that one with the formula. Let's do another one with the formula. This one, example F. So I've got 1 minus 1/2 plus 1/4 minus 1/8 plus all the way down to negative 1 over 512. Okay, not so bad. Except there's going to be one annoying thing about this compared to the one we just did. And I'll let you see if you can't figure it out. First things first, what kind of a sequence am I dealing with? Or what kind of a series am I dealing with? Geometric. And we know that because to get from one term to the next, you're multiplying. You can see it really easy here, right? What are you multiplying by? R equals
Negative 1/2.
-1/2. And then when you look at the next two terms, R equals -1/2 again. In fact, it's not a bad idea just to multiply by -1/2 in your mind and see, oh yeah, it works out the same. So if I want to find the sum of these terms, S sub n, A sub 1, 1 minus R, that's 1 minus R to the nth power over 1 minus R. And I need to squeeze in an n up here. N. I got a problem. I know what A sub 1 is, it's 1. I know what R is, it's -1/2. What don't I know? Yeah, I need to know what n is. So n is the value that's going to give me this last term. And that last term has to be in the form A sub n equals 1 times -1/2 to the n minus 1. Now normally I'd say, oh, this is a great chance to practice your logarithms because you've got, you know, an exponential equation. Essentially what you've got is -1/2 to the n minus 1 equals -1 over 512. Take logs on both sides after you get rid of the negatives. Well, but you know what? Let's be practical. That's a lot of work. I'm sure my colleagues might not necessarily appreciate this, but for such a small number like this, let me show you a different approach. -1 divided by 2 raised to the n minus 1. I need to figure out where that's going to give me -1 over 512. What's that decimal look like? -1 divided by 512. All right, it looks like that. Let's go to our table function and plug in some values. Now none of these look good. In fact, they don't even look close. So let me jump up to 8. -0.008. Yeah, that's still not enough. 9. Nope, not there. 10. Well, wait a minute. Looking close. If you zoom over onto that number, you'll see it's exactly what we needed. So n equals 10 is where we're at here. So is true when n equals 10. I'd probably make a problem like this a little bit more user-friendly on an exam. But in any case, n equals 10. Let's see about figuring out what s sub 10 is then. S sub 10, I don't need the 1 here. It's going to be 1 minus -1/2 to the 10th power divided over 1 minus -1/2. This is a challenge to put in on your calculator. You have a lot of parentheses and some exponents and then the negatives. So let me show you a little bit more user-friendly way to do this. So we're going to start by storing. Actually, no, I'm going to change my mode back to regular function mode. So I want it in that mode. Let's clear that, clear this. So the trick that I would give you is you're going to take -1/2, -1 divided by 2, and store it in x. So that's where we're going to start. Good there? And now I want to type in the formula for s sub 10, except that everywhere I see the -1/2, all I have to do is type in an x. It's going to make it a lot more efficient in terms of calculating this formula. So it's going to be parentheses 1 minus x raised to the 10th power. Get out of the exponent with a right arrow. Parenthesis divided by parenthesis again 1 minus x. A lot more user friendly than if you had to type it in with that -1/2 and worry about extra parentheses and all this other stuff. It'd be a royal pain. What fraction is this? Hit the math key, press enter twice. 341 divided by 512. That's the number that I want to see on an exam. I don't want decimals. There's a problem with decimals, and that is sometimes you can do the wrong thing and get a decimal that's pretty close to the right answer. So that's why I don't want decimals on something like this. Are we okay with that example? All right, that's a resounding yes. Appreciate the vote of confidence. Thank you. Let's try another one. And this one's kind of amazing. Let's see. So we just calculated s sub n or actually s sub 10 for our previous example. We summed up the first 10, or first 5, and then the first 10 numbers of a geometric sequence. But if the absolute value of r is less than 1 in a geometric sequence, then S sub infinity equals 1, no, excuse me, equals A sub 1 over 1 minus R. What on earth does A sub infinity mean? That's pretty bizarre. What is A sub infinity mean? This is cool. This is really cool that you get a glimpse of this kind of stuff. Let me show you A sub infinity, or what it means, with example H. So I'm skipping example G for the moment. Example H. Looks like this. No, I'm sorry, I shut it down too fast. Yeah, there we go. 3/5 plus 9 25ths plus 27 over 125 plus dot, 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 dot. What does that dot, 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 dot mean?
Infinity.
Means going on and on and on forever. It means never ending. So that if you wanted to sum this up, that would be S sub infinity, summing up all of these, which is remarkable. There's an infinite number of terms, and yet somehow you're able to find this. And in fact, let's see if we can't find this. Now, one thing that has to be true is that you have to have a geometric sequence. So do we have a geometric sequence here between these numbers? Well, if you calculated it, this divided by this, you get R equals 3/5. And then if you calculate it over here, you get R equals 3/5 again. So awesome. This is a geometric sequence. R equals 3/5. Actually, the formula for S sub infinity is actually easier to use than the formula for S sub n. All we need to do is type in S sub infinity is the first term, which is 3/5, over 1 minus 3/5. And why don't you see if you can't calculate that on your calculator? Tell me what answer you get. It's going to work out pretty even. Not exactly a whole number, but pretty even.
1.5.
Yeah. 3/2 or 1.5. Are you able to get that on your calculators? All right. Nice. Okay, so a couple spin-offs on that. Example I. I love this formula. So when you're looking at the limit of this, as the number of terms approaches infinity, you can actually calculate that. So here's the joke. An infinite number of mathematicians walk into a bar. And the first one says, I'll have a beer. And the second one says, I'll have half a beer. And the third one says, I'll have a quarter of the beer. And so on. And the bartender stops him and says, stop. And he pulls out 2 beers and hands it to him and says, here, you know your limits. Let's find out if the bartender was right. So this is a geometric sequence, right? So what does R equal in this? What are you multiplying to get from one term to the next? 1/2. And then 1/2 again. So it's a geometric sequence. This only works for geometric sequences. You can't sum up an infinite number like this for an arithmetic sequence. It's not going to happen. All right, so S sub infinity is going to be A sub 1 over 1 minus R, which is what? What happens?
1 over 1.
1 over 1 minus 1/2 which is gonna be 1 over 1/2. Was the bartender right? Yes, he was. So it sums up to 2. Pretty cool. Did you ever notice how cities and countries compete for big ticket events? Like, what's a big thing happening in sports right now other than Michigan made the Big Ten championship for the 2nd year in a row and won? FIFA, the World Cup, all right? So the World Cup's a big thing, brings in a lot of people. Detroit hosted Super Bowl 40, and the NFL estimated that it brought in about $90 million, or no, $50 million. So let's take a look at that. Let's see. Example J. $50 million was spent directly in the city. Now that $50 million is going to be spent in buying gasoline, hotels, restaurants, bars, etc., souvenirs. So a lot of that money gets respent. And of that $50 million, let's say 80% of it gets respent. So it's 50 million times 0.8. That's how much of it gets respent. And then that money gets respent again. So it's 50 million times 0.8 times 0.8 again, or 50 million times 0.8 squared. Can anyone guess what the next term would be? Yeah, and it gets respent again and again and again, and so on, all the way down. So what's the net economic impact of that initial $50 million? Well, can anyone tell me what kind of a sequence this is? It's geometric. Because you're multiplying by 0.8 to get from one to another. Now keep in mind another thing, the absolute value of r has to be less than 1, and it is. R in this case is 0.8. What's a sub 1?
$50
50 million. So if I want the net economic impact, then what I can do is I can calculate S sub infinity is going to be 50 million divided by 1 minus 0.8, and this should be a pretty eye-popping number. I'll let you calculate it so I don't spoil the surprise. It's called the economic multiplier effect. That is, when you have a big infusion of cash into economy, it gets spent and respent and respent and respent. Now this model may not be completely accurate, but it gives you an idea of what such a big ticket event can do. What are you getting? $250 million. Wow, that's starting to be pretty impressively large. Now, if you assume that this number is 0.9 as opposed to 0.1, then this number would have been 500,000 or 500 million. You know, and depending on the value you use for R, this can be bigger or smaller, but it has a big impact. Now, the one thing you're going to have to look out for on your homework is this. Something like the last example down here, and let me see if I can't make that a little higher on the screen. I couldn't use my formula on this geometric sequence. Can anyone tell me why? Well, the big requirement to use this formula is this right here. The absolute value of that common ratio has to be less than 1. If it's not, bummer. And in this case, R would be negative 1.4 So it doesn't satisfy the conditions to use that summation. You can't sum the series. It'd be what's called divergent right here. That's what happens here if you tried to sum that up. But that'll do it for section 12.3. Comments or questions? Awesome. Good luck and see ya.